Okay, let's begin. Still a lot to get through today, but hopefully we'll get to some. Hoping we'll start at least linear transformations today, which is kind of one of the most important things. But before then, let's define some terms. We're moving on to 4.7, where we're going to talk about the row space, column space, and the null space. Of matrices. So let's do a definition. Let A be a matrix. Do we do rank? I think rank. We're just going to read the dimensions. Okay, so that's the next section. Make sure. Let A be a matrix. Let's define it to be n by n. Later on, I'm going to tell you about some things that only work for square matrices, but for now, let's do it. Matrix over R or C. And remember, I can write that as F if I want to say R or C. Okay, so the subspace of Fn spanned by the row vectors of A is called the row space. The subspace of Fm spanned by the column vectors of A is called the column space. And the solution space to AX equals 0 is called, this I think we defined last time, called the null space. So these are some very important subspaces, and you'll see why they're important when we get to linear transformations. But let's do some notations. So the row space of A, we call that row A, column space of A. Call it COL A, and null space of A. Equals null A. these guys form what we call the fundamental spaces of A. Why they're called fundamental? Because remember, linear algebra is the study of linear transformations on vector spaces. It turns out we can tell a lot about vector spaces by knowing about these spaces, and that's why they're fundamental. Which in 4.10 is where we're really going to start getting to that, which is why I kind of want to rush to get there, because too much to so let's talk about how do you find them. We can talk about first some facts. That probably aren't obvious at first glance, but I'm not going to prove them. Row operations don't change the row space. It's also true that row operations don't change the null space. It's also true So here's something we know about row operations. They actually won't change your row space or your null space. The intuition from this comes from the fact that we can use row operations to solve equations. And for example, the solution set to where a set of equations equals 0, obviously we know that won't change under row operations because these were operations for the purpose of solving equations and not losing any information. It turns out though that row operations may change the column space. Because while row operations keep the rows intact, they don't keep the columns intact. So for example, a quick example here, we can look at a matrix like this. Is that a nice example? Something like this. So if you look at something like that, right? Notice that the column vectors are 1, 1, and another column vector is just 0, 0. What is the space spanned by this guy? How would you describe the set of vectors that can be spanned by these two vectors? What would they look like in R2? Yeah, but which line?
The line of slope 1.
All vectors on the line y equals x. So basically it'll span things that look like x comma x such that x is in R. Right? However, if you do a row operation on this, let's say I took row 1 minus row 2, what space do the column vectors span now?
Anything on the x-axis.
Only things on the x-axis. So this guy would span things like x0 such that x is a real number. So in one case, the column vectors spanned anything along the line y equals x. However, doing a row operation killed that, and now it only spans anything along the x-axis. So row operations can affect your column space, but they actually won't affect the row space or the null space. So that kind of gives us a hint on how we want to find these spaces, we can actually use row operations. What we do know is that row operations will maintain independence and all that. Of the row vectors, not necessarily the column vectors. And so we can actually just identify these two guys. Well, we can ultimately identify all of them by row space, but when we're looking at for the column space, we have to do one extra step, or one back step, it seems like. Okay, so to find these, use row operations. So that's what we're going to do, but we're going to be careful with the column space. So put A into row echelon form or reduce row echelon form, either one will work. And so here's how we find it. The non-zero rows of this form of A form a basis for the row space. Because essentially what would happen, if any of the row vectors are dependent, you can use a row operation to kill the dependent rows. So any rows that are dependent will automatically become a row of zeros once you put it in row echelon form. And then the matrices that are the row vectors that are left over, they would span the same space by the plus or minus theorem. So you can just use row operations to kill the redundant rows, and so the space spanned by the remaining rows would be your row space. If you use the reduced row echelon form or row echelon form to solve, and this we did last time, this augmented system. So once you put it in reduced row echelon form or row echelon form, you can just pretend that the vector that you're setting it equal to is zero, is the zero vector, and then you find the solution to that. And the solution space to this is the null space, is a basis. Well, the solution space is the solution space is the null space, which means the vector solutions to this form a basis for the null space. Finally, for the column space, we have to be a little bit careful, is that now you look at not the reduced row echelon form, but the reduced row echelon form will hint you which vectors you want to choose. The columns in A, as in the original matrix, that correspond to the non-zero columns in the reduced row echelon form. Or the row echelon form. Form a basis for the column space. So by doing row operations, you might kill certain properties that the column vectors have. So once you identify the columns that won't die, the ones that are not dependent, you have to actually look at the original matrix to find the original space that will span, because doing a row operation might change that. And so that's how you can get a basis for the column space. And essentially, once you have a basis, you have everything. The basis tells you how to construct any vector in that space. So being able to, yeah?
Couldn't you take the transpose matrix and treat it like you would like finding your row space?
You could do that. So if you didn't want to if you never had to find the row space in the first place, if all you were interested in was the column space, you could transpose it and find and do row operations. That's also true. We could find a basis for the column space by finding a basis for the row space of the transpose. Right. So you can turn the columns into rows and do row operations, and that way it maintains their integrity. However, if you had to find the row space in the first place anyway, you would have already done a lot of row operations. You don't want to redo a bunch of them, so it's easier. But if the column space is what you're after in the beginning and you didn't have to find the row space, then yeah, you could use row operations by first taking the transpose. And it's important to compute these, so I'll give you an example of a problem that I could ask, or will likely ask, on like a test, or on the final. This is just, I'll give you a matrix, and I'll ask you to find a basis for the row space or the column space or something like that. And it just involves you doing row reduction. And I might ask you to do something else after that, but this is a question on its own it's worth asking. So I can do an example. Find a basis for the row space column space and null space of. So here's the matrix. So if I ask you about that, I'm going to skip ahead. What you would have done is find the row echelon form or reduce row echelon form. Ultimately, after several row operations, it's probably not as, this one is probably less than you would think. I know it looks like a large matrix, but I chose the number so that this will actually work out relatively quickly. But at the end of the day, this is the reduced row echelon form. Now assume you can get to that form. Now tell me the answers to the question. So I can give you a matrix and I can ask you, find a basis for the row space, the column space, the null space. Here's the matrix. So with that matrix, you're going to just find the reduced row echelon form using a bunch of row operations. Once you get it to, and row echelon form is fine here. I just gave an answer in the reduced row echelon form. Just in case you guys want to check, you can all get to ultimately the same answer. So let's do that. What's the basis for row space? It's literally just you take the non-zero rows. So 1, 2, 3, comma, 0, 1, 0, minus 3, 6, comma, 0, 0, 1, 0, 0. That set forms a basis for the row space. I just pick out the non-zero rows, essentially. What guys, where do these guys live? In R5. So notice that this is, the row space here is a three-dimensional subspace of R5. We'll talk about that in a bit. What is a basis for the column space? This is not official notation, I'm totally making this up. B subscript R and B subscript C.
Isn't it the whole original matrix, the column vectors? Because none of them are non-zero. I mean, none of them are zero columns in reduced version.
I think I neglected to say something in the definition. Because it turns out that these two are dependent. So the idea is
Oh, it's only the ones with pivots.
it's only the ones with pivots. So add that to the definition. I think I neglected to write that down.
It's a three-dimensional subspace of R4.
And that would form a three-dimensional subspace of R4. But again, with the column space, it's kind of weird because row operations can affect how the vectors relate to each other. So what you have to do is you have to look at the corresponding columns in the original. And those are the guys you would write down. Because your row operations might mess things up in the columns. So it's 1, 1, minus 2, 1, comma, minus 2, 1, 1, minus 2, comma, 1, 2, 2, minus 1. So these guys live in R4. So I'm going to make some comments in 4.10 where it's going to make sense why I'm even pointing this out. Because it has to do with the domain and the range of the function that we're going to be looking at and how it behaves on these vector spaces. Another thing you can notice here is that you might notice how I know I only needed the first three. Another way you can kind of check quickly is that in this case you can kind of see that these three columns are all multiples of each other. You notice that? So what happens is I can only pick one of them and throw away the other two, which is what ended up happening when I got here. So that's why you only care about the guys that have the pivots. So the guys that have the pivots, the rows with the pivots, you can take those exact rows and they're a basis for the row space. If you take the column with the pivots, corresponding to the original matrix, those form a basis for the column space. Because it will get rid of dependent columns at the same time. Yeah.
Why don't we correspond row space to the original?
You could, but it would be unnecessary. The relationship between these and those are going to be the same. But this is more of a reduced form. There are more zeros, they're easier to deal with, they're nicer to deal with. We'd love to be able to do that with the columns, but the row operations kind of mess it up. So we're forced to go back to an uglier representation of these vectors. But if I said, instead of these three vectors, if I took three of the originals, I would still form the same space, but the numbers would be uglier.
If you did the transpose method, though, you could have a cleaner version.
Right, so if I did the transpose and did the row operations, I could have a cleaner version of this. If that's important, then you can do it. But you have options here. That would depend entirely on context.
No question.
Yeah.
How come is that when we're doing the basis for the column space, we'll use the original equation, but when we're doing it for the row space, we're just using,
Yeah, that's what I mentioned. That's what the facts over here, what I wrote, were about.
it affects.
Row operations do not affect the row space. So whether I take the guys down here or the guys up here is irrelevant. However, row operations do affect your column space. So identifying the columns that are not dependent here, I can't take those vectors, I have to take those vectors. Because there's no guarantee that the space spanned by these three vectors will be exactly the same as the space spanned by those three vectors. But with the rows, they will always share that same relationship. Okay, what about basis for the null space? So essentially in the null space, what you would do is you would pretend that what you were trying to solve was a homogeneous system of equations, right? So you kind of pretend that this here is augmented with 0, 0, 0, 0. And now you try to find the solution space to that. And so what would the solution space to that look like? Let's say I named this x1, x2, x3, x4, x5. How do we read off solutions from this?
X1 equals 0.
X3 equals.
Well, let's remember the procedure. Let's be very algorithmic about it. Remember the first thing we did was to identify the pivots. Guys without pivots get to be parameters. So that first step, I would say x4 is equal to t, x5 is equal to something else like r. And then you read from the bottom row up. So in row 3, you would get that your x3 is equal to 0. In row 2, you would get that your x2 minus 3x4 plus 6x5 is equal to 0. So in other words, your x2 is going to be 3t minus 6r. In row 1, you get your x1 equals 0. And so what that means is your x1, x2, x3, x4, x5 would be equal to x1 is 0, x2 is 3t minus 6r, x3 is 0, x4 is t, x5 is r. And so you can split this up. And you'd be able to write this as, if I throw in the constants here, those are just 0, 0, 0, so I can actually even ignore that if I wanted to. Plus t times this plus r times that. Coefficients of t are 0, 3, 0, 1, 0. Coefficients of r is 0, minus 6, 0, 0, 1. And so these two vectors form a basis for the null space. So this means a basis for the null space would be 0, 3, 0, 1, 0. 0, minus 6, 0, 0, 1. So the null space is a two-dimensional subspace of R5. Right? So any vector, so you look in R5 and you look at the plane that is spanned by these two vectors, every vector in that plane will be a solution to AX equals 0, where A was the original matrix that I gave. And that plane would of course pass through the origin, that's why there's no point. And in fact, do I want to just show you that? I guess that would be nice. I already erased A, but let me recopy it here. So that's how you fully solve a problem. So I give you a matrix, asks you find a basis for the row space, column space, null space. This is how you do it. Find the row echelon form. You don't have to go all the way to reduce the row echelon form, but you find a row echelon form, and you can take out all the rows with pivots. That's a basis for your row space. Figure out all the columns that have pivots. Take the corresponding columns from the original. Those form a basis for the column space. And then you pretend that you are solving a homogeneous system, and the guys that are attached to parameters will be a basis for the null space. And there are several uses to doing this. We'll see more in 4.10. Here's one. Let's say you had a different question. Find a basis for the space spanned by, if you're given 5 individual vectors. And you were asked to figure out what space do these guys span, find a basis for it. Then the answer would be the same as the column space of A in the previous example. Notice that what I just did, I took the individual columns of A. So you could have been given these as 5 separate vectors in R4, and the question is, what space do these guys span, right? And you'll notice that they only span a 3-dimensional subspace of R4, which means, for example, I could not take this list of vectors as a basis in the previous example. By the way, we can also see, V1, V2, V3 form a linearly independent set, right? Which means that the V4 and the V5 were redundant. So if you had to throw away some vectors, you would throw away V4 and V5 because they're not important.
Because of
Yep.
scalar multiples?
Because they would be scalar multiples of one of the other ones. In fact, we can know which so while we see V4, V5 are dependent, in fact, we can figure out dependency relationships by looking at the reducer echelon form. Just to remind you what that is. So it's 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, minus 3, 0, 0, 0, 6, 0, 0. So once you put it in this reduced form, what you can notice is that this one here, this is minus 3 times the second vector. This one here is actually 6 times the second vector. So in fact, not only can you identify who's linearly independent, you can also figure out what the linear relationships are. You could say, you could conclude that V4 is actually minus 3 times V1, and V5 is 6 times V1, V2. That's a nice little thing you can do. Here are some more uses. And again, when we get to 4.10, this is actually going to make a lot more sense.
Professor,
Yes?
whenever you say find a basis, it automatically means column space.
No, it doesn't automatically mean that. But you could answer that question by doing this, by throwing them in the columns of a matrix and then finding the column space. But no, but by find a basis, what that means is you have to find a set of these vectors that are all linearly independent, and they would span the space. Yeah.
If you chose to write the matrix as those vectors in the rows, though, then you would be looking for row space.
Then you'd be looking for the
Because
space.
you're looking for basically like whatever space is parallel to the way
Yeah.
you set the vectors. up.
Exactly. More uses. AX equals B is consistent, meaning this thing will only have a solution if your B is an element of the column space. That means the column space kind of identifies what your possible outputs can be. And here's a nice theorem, and I'll just mention, this is going to be the last thing I'm going to mention in this section, and I'm just going to draw a nice little parallel. Theorem. Write this down. Let AX equals B be a system, and X naught be any solution to the system. And furthermore assume that say V1, V2, Vn is a basis for the null space. Then any solution can be expressed let's call it solution X. Any solution X can be expressed in the form take that point, and you'd be able to find scalar C1 up to Cn such that any other solution will be that point that you already know is a solution plus a linear combination of the basis for the null space. And it's even more general. So if you have a solution, it's definitely expressible as that form. Furthermore, it kind of goes the other way. Moreover, for any choice, if you randomly choose numbers C1 through Cn, then if you create a vector by taking x naught and then choosing that random set of scalars here, will also solve the system. So the idea is, if you know something is a solution, you can write it in this form. Furthermore, you can use this form as a template for all solutions. Literally, if you choose any random scalars here, where the v1 through vn is a basis for the null space, you'll automatically form a solution by doing that. And of course, the idea is, if you multiply the matrix by this, you can expand the matrix, and then you can factor out the scalars, and then this, since this is a basis for the null space, A times this would be the zero vector. So you're adding a bunch of zero vectors, and this is already a solution, blah, blah, blah. So actually writing out the proof for that wouldn't be that hard, but I don't want to take the time. Does anyone kind of can draw any parallels from this? Does this remind you of anything? Yeah?
Linear combination?
Sure, it's linear combination, but from another class, maybe. Yeah?
Series? Infinite series?
In what context?
Summation?
I don't. Yeah, but what would that have to do specifically with null space and all that stuff?
In calculus 3, we did something similar.
Yeah?
Kind of like a linearization in calculus. You take a point you know and then you find a point nearby.
A linearization? Sure, you can put it in the context of linearization if you're looking for a linearization that happens to pass through the origin, then you can think of it in that context, sure. I was thinking more again, and I guess not a lot of people took this, but differential equations. For those of you who've taken that. Remember there was if you have a linear differential equation, then the solution was, you had to find a particular solution plus the homogeneous solution. Do you guys remember that? And the homogeneous solution was just a linear combination of n functions that solve the homogeneous case for the differential equation. And then if you can find any one solution for the particular solution, then the general solution was the particular solution plus C1 times the first homogeneous plus C2 times the second homogeneous, et cetera, et cetera. You could like literally prove that entire equation in linear algebra, right? Because the solutions to a linear differential equation form a vector space. So you can literally correspond every solution to a linear differential equation as a set of vectors in Rn if you have an nth order linear differential equation. And so it guarantees that this is what the solutions have to look like. And this will be the only solutions this will be the only way to write down a solution uniquely. So I thought that was nice. There are a lot of theorems in the differential equations regarding the solutions to a linear system that it's all linear algebra. You can prove it with linear algebra in the background. And more complicated things than that, basically we need more stuff for you to really fully understand how that would happen. But essentially you're going to create a function from Rn to the set of all possible solutions to a linear equation. So you can associate a vector with all these solutions, and then you can arrange these vectors now as columns and rows, and you can find the null space for that particular linear differential equation, and then this kind of falls out right away. So there are theorems in your differential equations class where they say, this is what the solution has to look like. And this was actually a pretty nice way and a relatively easy way with minimal calculus by which you could actually prove that theorem. But yeah, we'll get to more uses here. Let's actually go to 4.8. We're not going to spend a lot of time here. I just want to define some terms and then extend our equivalence theorem. Let's look at rank, nullity. I mean, I already mentioned the fundamental spaces. It says and the fundamental space, but I'm not going to talk about that. Rank and nullity is pretty much what I want to talk about. So let's do a definition. A and by n be a matrix, then if you take the dimensions of the row space, this is what we call the rank. What you can note is, dimensions of the row space. Remember, that's guy, after you put it in reduced or echelon form, those are the guys with the pivots in the rows. So it's equal to the number of pivots.
So the last one was 3. The last example we did, what we found.
Yeah, so in the last example, the A I put over here, you could say the phrase, the rank of that matrix was 3. And that's just basically you saying, if I find the reduced or echelon form, there will be 3 non-zero rows, and that's the dimensions of the row space. It turns out, you can also note, that this is exactly the same as the dimensions of the column space, because for the column space, you were also counting the number of rows, the number of pivots. So the dimensions of the column space and the dimensions of the row space happen to always be equal. They both actually depend on the pivots. And so that is called the rank. The dimensions of the null space is called the nullity. So that's the next definition. The dimensions of the null space of A equals the nullity of A. And it's denoted, you write out the word nullity and you put A in parentheses. So that's the notations. Oh, here's a theorem. It's called the dimension theorem. It's a major theorem, but it's not that hard to prove or actually to see why it's true. But the rank plus the nullity is equal to number of columns, n, where n equals the number of columns in A. That's called the dimension theorem. Notice that the rank is the number of pivots you would have. So if you find all of those, you find all the columns that have pivots. The nullity actually came when you assigned parameters to the other guys. So the number of parameters plus the number of pivots actually gives you the number of columns in total. So you can always figure out one as opposed to the other. So the dimensions of the column space of a matrix you can always split into 2, where whatever dimensions you assign for the rank, subtract the number of that from the number of columns, and you actually get the dimensions for the nullity, or vice versa. Because this guy comes from the number of pivots, and this guy comes from the number of parameters or free variables. Add those up, that's the total number of columns. I also put a note here. Rank of A happens to be the same as the rank of A transpose, because the column space is the same as the row space of the transpose. It'll be the same number of things. Okay, so with this we can expand our equivalence theorem, which is going to help us learn some nice thing about functions for pretty much for free. So with this we can expand. So the equivalence theorem is a super important theorem in linear algebra. A lot of effort is meant into building this theorem up. Put a lot of energy into it, and that's because a lot of useful facts fall out of it very nicely. So that's the theorem that talks about. The following are equivalent for a square matrix, and they have a bunch of lists of stuff. As written here, I think it's a summary of 4.8.8. But you won't have to remember that. Just say the equivalence theorem and I'll know what you're talking about. If you have to use this in a proof and you want to mention this. So let A n by n be a matrix. Notice that it is a square matrix. The following are equivalent. One, A is invertible. Two. Can you guys tell me some of the others quickly? The term is not zero. What else can you tell me? This isn't exactly the order I wrote it in, but let's just go anyway. That means it's invertible. What can you tell me about the reduced row echelon form of A? It becomes the identity, the n by n identity. What can you tell me about the system AX equals B?
Consistent.
Has a unique solution, only has one solution. In particular, they put this as a separate thing, but this, you can know it is consistent. It will have some solution for any n by 1 matrix B. In fact, for each individual matrix B, it will have a unique solution. What can you tell me about AX equals 0? Has only the trivial solution. So these are all equivalent. So at any point, if you know one of these, you know all of them. And if in any proof you know one of these and you want to use any of the other facts, you can just say, by the equivalence theorem, this is true, right? So if for some reason you know that A is invertible and you need to talk about determinants, you can say, by the equivalence theorem, determinant is not equal 0. And I will believe you. You won't have to explain any more than that. Just invoke the equivalence theorem and it'll be good. Now, the rest of it, I believe that's all the ones that we covered so far. There's one more, but if G. A is a product of elementary matrices. We don't use that very often in practice. That's more of a theoretical crutch, where it's easier to prove a lot of things using this fact. But here's something that based on today's lecture we can now start talking about. H. What can you say about the rank? It's equal to n. What can you say about the nullity? Equal to 0. What can you tell me about Hij? The row vectors of A span the entire space, Rn or Fn, to be more general, who can work for real or complex numbers. What else did I want to ask you? In fact, we can say something stronger. I think in the book they listed it out one by one, but I summarized it when I wrote it down. The row vectors of A form a basis for Rn. Which means, of course, they both span and they're all linearly independent at the same time. Right? So you can get, I can state two facts in one. K. What can you say about the column vectors? You can actually say the same thing. They also form a basis. So this is a matrix over F, meaning the components in the matrix come from the real numbers or the complex numbers. And you can get all of this for free. And particularly what that kind of means for functions, I don't know how far I would get into that if I started it right now. Frankly, that's the next one. What this would kind of mean for linear transformations is that, for example, knowing that this guy has a unique solution can sort of tell you when a function is one-to-one, right? Knowing that also that is consistent for every matrix B, meaning that any B I take in Fn, I can solve this equation with that, sort of means that if I think of A as a function, it will also be onto. Right? It will be surjective. Every element in the codomain will be an element of the range. And if I know a function is both one-to-one and onto, what do I know about the function? Huh? It has an inverse function, which kind of means it, right? What else do I know about the function? It's bijective, that's the name for it. So a function that's one-to-one and onto is also bijective. What can that tell me about the domain and the codomain? They have the same number of elements. And when I actually define this as a linear transformation, which I'm going to do next time, you will see that not only do they have the same number of elements, but they will all function the same way. Doing manipulations in the domain will be equivalent to doing manipulations in the range. So for example, adding 2 elements in the domain is the same as adding 2 corresponding elements in the range. So not only will they have the same size, but they'll have the same behavior in terms of the operations. Multiplying a domain element by a scalar will correspond to multiplying its corresponding range element by that same scalar. Right? So knowing these, so if I can say, oh, my A is representing some linear transformation, and I'll tell you specifically how we can make that happen. If I know that I have 2 spaces where I can take plug-in vectors from a domain, it will output vectors in this guy, and I can represent that with a square matrix. As long as I can look at that matrix and talk about any one of these. If I know any one of these, I can know a lot of information about the functions and the sets that the functions are operating on for free. Right? So, and that is super powerful. That allows us to study a lot of things, and we can get away with talking about them because we were just playing around with arrays of numbers the whole time. Yeah?
So, I get the feeling that you could, if you
found the reduced row echelon form, you could describe a restriction such that your function would then be a one-to-one function on that restriction.
Yes, in fact, so let's say you have, but yes, so let's say you have this guy as your domain and your function comes over here to your codomain, but it doesn't hit everything. Then yes, using that, you will be able to say, here is the range of the function. It is this dimensional subspace of the codomain. And you can restrict it so that from the domain to that new set is now a function, and you can study the subset of this codomain, which again, in turn, can tell you a lot about the codomain itself. But that would again require you to talk about the vectors. But it's a very nice thing. And in fact, at the end, we will talk about a function that preserves the operations of a linear transformation and at the same time goes between two spaces, which by the way, they will have the same number of elements, they will have the same number of basis vectors, dimensions will be the same. Like, once this holds, once you can describe a function with a square matrix and it's invertible, dimensions are the same. They're the same number of elements. In fact, you can literally think of them as the same vector space, regardless of the fact that the elements might look different, they might behave different. In other words, in some sense, looking at Rn and looking at a set of differentiable functions, no difference. There's no difference between the two. Like, if I know something about one, I know something about the other. And that kind of abstraction makes it a very powerful technique. I can just play around with matrices and I can talk about solutions to differential equations. I can talk about integral functions, differentiable functions. I can talk about projections, rotations. I can talk about so many things that are just an abstraction of Rn. And they're literally exactly the same guys. It's kind of like they went into witness protection and so they changed their identity. But you know, it's the same guy. Yeah, but my name is John now. No, you're the same guy. That's kind of what it is. Right? So this is a very powerful thing. So knowing this equivalence theorem and you apply that to functions, it's some amazing things happen, which we'll start to see in 4.10 and in chapter 8. But for now, we'll stop there. Yes?
So you said if we know just one of these, then we can assume that it's a...
Yeah, that's what equivalent means. It means everything in the list is true at the same time, or they're false at the
But
same
we
time.
would know if it's an n by n matrix, right?
Yeah,
Okay.
yeah. We're going to talk about, first of all, how I would represent a function as a matrix, and how you would know that it's a square matrix or not.
Are
Yeah.
we having a test on Thursday?
This Thursday?
Next Thursday.
No, I think next Thursday is the talk.
Oh, yeah.
So
Tuesday
we'll probably have a test on Tuesday, and the following